Okay, so our first speaker is Dr. Dave Patterson. He's a professor emeritus of computer science at UC Berkeley, distinguished engineer at Google, and vice chair of the board of directors of RISC-V Foundation. Of course, he's well known for his pioneering work in RISC, RAID, and NOW, and he's, of course, also very well known for his classic textbook that all of us have read. Dr. Patterson is a member of the National Academy of Engineering, National Academy of Sciences. He's an IEEE and ACM fellow, and he's received many teaching and research awards, and of course, most notably, the Turing Award last year. So we're excited to have Dave kick off our workshop. He's going to be discussing how open and agile hardware design can potentially be a critical component in a new golden age of computer architecture. Dave?
All right.
Let's welcome Dave.
I gotta say the organizers did a great job. That's an amazing lineup. I would have bet you couldn't have got all those people here. So good job. I'm actually giving 3 talks today at various things, but the one slide that's in every single one is this one. Just still people who claim Moore's law survives, right? So Gordon Moore, it's pretty clear what he wrote, right? In 1965, he said double the number of transistors every year, and he amended it in 1975 to doubling every 2 years. And if the slower one were true, we'd have 15 times as many transistors on the latest Intel processors every day. So we are in the post-Moore's law era. So hopefully we won't have to argue about that in the workshop. And we all know about Dennard scaling. You know, how could you put 100 times or 1,000 times as many transistors? Wouldn't it burn up? Well, because we would scale down the threshold, but we can't voltage. We can't do that anymore. And the thing that most people think of Moore's law as faster processors, that's over, right? You buy a new processor from Intel or AMD, it's really not much faster than it was last year. Maybe it'll take 20 years for it to double. And then in terms of things to keep you up at night, you know, then we found out that we're providing ways to attack computers by the way we build them. Not the software, which everybody thought was the weakness, but the microarchitecture itself. Okay, so what opportunity, what's left? And for this thing, you know, I was jealous of my friends in operating systems and compilers and databases, because they could work in industrial strength things, and they and their students could make contributions to something that everybody in the world could use. Why couldn't that happen in architecture? And that kind of led accidentally to RISC-V. RISC-V was actually led by Krista Sanovich and Yunsuk Lee, who's here, and Andrew Waterman, and I gave some help. It was actually created for us. It started in May 2010. We didn't want to keep doing the same instruction set architectures because we make a change to it and then all the potential benefits there. So they decided to start from a clean slate in May 2010. And so what's different about it is, first of all, free and open. Anyone can use it. And I think, kind of not surprisingly, what that means, there's more competition, which is going to mean more innovation. So probably right now, so I guess, you know, we've been kind of pushing RISC-V publicly for 4 years now, but probably there's more companies building RISC-V processors than any other architecture. That's probably true. So I think we're just going to see more innovation in that space because it's free and open. Not surprisingly, it's for the cloud and the edge. You know, we have 32-bit versions, 64-bit versions, and there's versions that are focused on, you know, even fewer registers that the tiny embedded need, as well as people thinking about 128-bit stuff. But you can fold that into an instruction set. One of the drivers of the interest of the opening is this security, kind of worldwide interest. Once people found out that people were putting things into commercial chips that the customers didn't know, people wanted to start designing their own secure core. So to do that, you need your own instruction set. And we have this idea that this workshop was promoting of actual open cores. So like, you know, downloading the Linux source code, you could see what's in there before you fabricate it. So that's another big plus in the modern world. It's actually a simple and modular instruction set, the thing that I've long promoted for instruction sets. And, you know, when you start 25 years later, you get to learn from the mistakes of others, and you don't make them from the things that were done in the 1980s. It's far simpler than ARM and x86. If you're just making not marketing decisions but technical decisions, there's no reason not to be simple. And the big thing is, with this modern world, is to be add custom instructions, and basically you need a big opcode space to support that, and they've got that. And finally, learning from our colleagues in the software industry about what you need to make open source work, it's just not going to be viable if you rely on academics to support it. That's not going to happen. So they have foundations, and we followed that and created a foundation. I'm, Krista's the chairman of the board. I'm the vice chair, and there's people from other companies on the board, from NVIDIA and Western Digital and others. I'll just tell you about the foundation. So in terms of popularity, it's up and to the right, more members every year. These are some of the ones you might recognize. Probably NVIDIA now has a RISC-V controller in every GPU, so that's tens of millions a year, and Western Digital is going to put them in their disk drives, so that's going to be billions per year. The countries where somebody's working on RISC-V, it covers most of the planet. We have a new leader, a woman who's directing it, Callista Redmond, who used to be at IBM. Hennessy and I put it in various books, so it's hard to avoid. And we've made them in, especially the RISC-V Reader, which is a slim book, in many different languages. And besides RISC-V, there's other efforts to do open instruction sets, in particular NVIDIA. So NVIDIA is doing, has done a inference chip, so there's training and inference or serving, and they've done a public domain version of their inference chip. So what does that mean? It means the software is open and freely available, the designs are open and freely available, the Verilog, and it's I'd say, adjustable design, parameterizable design, so you can change the number of units and stuff like that. And they just put everything out there for people to use. So that's another example. And I think when Richard talks about the CHIPS Alliance, I expect to see more things like this. There's a little bit of confusion about, is it an open source instruction set, or how does that work? So let me clear that up. Might be useful for this workshop. So there's really two things, right? There's specifications, and you can think of that like an instruction set, or like POSIX for operating systems. So that's the spec, right? Then there's implementations of the spec, kind of the source code, right? So for RISC-V, there's something called Rocket that was developed at Berkeley that people can download and use. And of course, there's the Linux source code. So there's specs and designs. Okay, and then there's three flavors, and then there's products based on those things, right? They download the design, they put it on their own boards. I'll tell you about one of them, or Red Hat software. Okay, so specs and designs, there's three options here. You make it free and open, that's what this workshop is about. That means there's no fees, anybody can use it. The consequences of it, that means if you've got the spec, you can design one yourself. If you design one for yourself, you can share it with others, or you can get it from others. So that's free and open. Licensable, which is a more traditional model, where the company owns it and you pay to license it, but you can't give it to anybody else because the company owns it. And then there's closed, which the company owns it, but nobody else can use it. Okay, so there's specifications and designs, there's three versions of it, so that's a matrix, all right? So we'll have the specifications be the rows and the columns will be the designs. So starting off in the right-hand corner, if it's a closed spec, the only option is a closed design. So like the Intel instruction set architecture and Intel microprocessors. And there's lawyers to make sure, get involved if you try and do that. Then there's the licensable model, like ARM does, right? And if you have a licensable spec, you can either get designs from ARM, or you can build it yourself. And roughly that costs about, for ARM, about $5 million plus 4% royalties per core that you have, if you want to get a design from them. But if you want the right to build your own, that's about $25 million. Okay, now the subject of this workshop, free and open designs. Well, if it's free and open spec, you can do three things, right? You can design it yourself, you can download it, you can share it. That's what people refer to as open source, right? But you need the free and open spec to do it. There are also companies like Sci-Fi that are also making licensable designs, and companies like NVIDIA who's doing a closed design. But you need the open spec to have the open source. So RISC-V is really an open specification, but you need that to enable free and open designs. All right. Okay, so an example of this is one that was done by one of Chris's and ours former students, Jiangxi Tan and his company. So give you an example of what we could do. He went from nothing to chips in 7 months. It's got, I think it's got a 64-bit version of the RISC-V and 12 accelerators, memory, and the whole thing sells for $3, which is just amazing to me. I think another challenge facing our field is security, and I think it's linked to open architectures. I think those things go together. The security community likes things simple and verifiable. They're worried about trapdoors, and so they want everything open. They don't believe in security through obscurity. But equally important is we need a lot of people. If we're going to make security really work, we need a lot of people to work on it, and by being free and open, anyone can work on it. And because we want everyone, people in academia and industry, for these other designs, they restrict who you can talk to. And then I'm excited about hopefully making progress by making security experimental rather than making security just kind of theoretical or critical. Given FPGAs, open source implementations, and open software, you can have a whole running system. And if you've got some great idea that you think will make your thing secure, you can try it out, put it on the internet. You know, it may run slow, but it runs fast enough software, and you could either reward people for successfully attacking it or just put it out there. So I think open architectures are going to be the vehicle of progress in security, and particularly probably RISC-V. And then, you know, a revolution happened in our software colleagues about 17 years ago. But, you know, if you go to the dawn of computing, software projects started crashing and burning right from the beginning, and people thought the problem was we didn't have good engineering discipline, and so we would go to civil engineering, because they build bridges, they don't fill down. Let's build software like we build bridges, so there became this elaborate plan and document approach, sometimes called the waterfall model. Software projects still went awry. You know, they were late or over budget or just flat never worked. That was still happening. So in 2001, a group of people went off on retreat, and they announced the Agile manifesto. It says, we're not going to do planning and documenting, we're going to build prototypes. We're going to go to the customer with the prototype and get feedback what we should do next rather than this elaborate method. So that was a very heretical approach to building software, but it's become very successful. So there's something called the Scrum team. It's kind of like rugby, 5 or 10 people. They sprint for 2 weeks to build the next prototype to show to people to get feedback on it. And then the good news is that I think the new CAD software enables imitating software developments, and particularly what you want to do with something like that is reuse designs, so agile hardware development. So this is a paper that Yunsip did, and so how can you do this in hardware? Hardware takes, you know, forever to design and forever, you know, months to fabricate. How does that fit with a 1-week sprint? Well, it's these, you know, hierarchy of design, right? If it's C++ simulator, that's software, you can change that easily in a month. FPGAs goes faster. You know, anybody in computer architecture in academia can do it now because it's on Amazon. You can probably even get free money to do it, but they have it there. But this lets you run for billions of cycles. Then putting it through the ASIC flow, so you can get ideas of layout and area. Unfortunately, you're not really done to be able to do that. So the Berkeley people talked about a tape-in that it's already, you could tape it out, you could fabricate it, and you'd probably get a pretty good idea about the area and power from that. But, you know, and you could stop there and write your papers. You know, that would be a very credible design. But that's such a dumb idea to stop there. You know, it's like training for a marathon and, you know, 26.2 miles. You train for it and you get there, you run 26 miles, you're 200 yards from the end, you say, well, I could probably do that in about 30 seconds, so I'll just stop here, right? And so all your work and the glory, you get the medals and all that stuff, you just, oh no, I don't need to do that, I know what it'd be. So the one thing we have advantage over our software colleagues, we make physical things, you know, and there's nothing as exciting. The chip comes back, you can show it to your parents, to your friends, you can put it on your lapel. How well is it going to work? Does it really hit the clock rate? What is the power really? So it's kind of like Christmas morning when it comes in if everything works. So, but only Cornell and MIT can afford this, right? No, no. It's, they've forever had test chips. Test chips have always been there, and they're little tiny chips, like a millimeter inside or a couple of millimeters. Well, where we are in Moore's law, That's millions of transistors. You can do a 64-bit RISC-V core and the NVIDIA accelerator on that little tiny chip. And what does that cost? It costs like $14,000. So fractions of what it costs to have one graduate student. So anybody can afford to do this as long as you keep the chip small, and there's a lot of advantages to keeping the chip small and making it easier to build. Now, if you really want to do a big chip takeout, you know, that's going to cost a lot. That will cost a lot of money, but you know, you don't need to do that to demonstrate a lot of the ideas. And it's still, even if you get a small chip back, it's very exciting. I think what I want to do, you know, just, you know, clearly a thing that's happening today is domain-specific architectures with the end of general-purpose processors getting faster. But I think what I want to do is, I think I'm going to skip these slides. And just mention that the, you know, kind of just putting it in perspective, the TPU v1, which I helped write up the case for, which Google did in reaction to this kind of potential of machine learning, was incredibly faster than commercial products, like factors of 30 in performance per watt or factors of 80. You know, usually for something in production, it's factors of 2 or 3. And I think it was just the case that with general purpose solutions, which weren't optimized for machine learning, there was just huge opportunities there. So factors, you know, so I think what's exciting is that kind of for general purpose computing, and a lot of the papers in this conference historically have been really small gains, because it's hard to make general purpose microprocessors, 5% gains, 10% gains. There's opportunities for big multiples in the domain specific areas, which is another reason to do this. Okay. And it's a particularly exciting time in just purpose architecture with all these different bets that are going on. It's really, I would say, it's unlike other things. The only other time in my career that was something like this was in the early days of multiprocessors, where there were SIMD designs and data flow designs, and these companies were starting. But yeah, today, you know, Google has been betting on 1 or 2 big cores per chip and these giant systolic arrays, doing 2D multipliers and software-controlled memory. NVIDIA has leveraged their highly threaded, you know, 20 megabytes of register kind of designs, and they're betting on that and keep going. Microsoft has popularized using FPGAs, putting in every one. Intel's kind of doing everything, right? They bought Altera and they bought these other companies. So, and then at least 45 startups in this area. And any idea that didn't work for general purpose computing is being tried now at some startup company to see if it's going to work this time. So it's an extraordinarily exciting time. And I think a lot of it is going to use Agile development and hopefully open architectures. So there's all these opportunities. I think open instruction sets are going to become a very significant fraction of the commercial future, which is great news for researchers. And I think Agile development just kind of makes sense, right? It makes more sense to do that. The way I did chips before was, you know, it'd be a PhD dissertation, and then at the end we get the chip back. And it makes much more sense to do an iteration, get it back every, you know, 6 months, do a new one, and go on to the next one and make it a little bit more ambitious. It's just common sense. And, you know, this need for domain-specific solutions to go forward is this opportunity. There's more architecture work needs to be done now, and that's why, and I think it's going to be a new age for computer architecture. All right, with that, I'm ready for questions. And there's, make sure you fill every seat in the back before you take any in the front. Some of you want to sit.
He's kidding. There's
You're allowed to sit.
There's plenty of seats up here.
Yeah. Okay, questions? Yeah.
Question. So like in your role, right, you have the free licensable and then the closed ones. So in your, of course, all of it depending on the community, but in your mind, what would be the ideal kind of proportion, right, for the community, right? How many comes from the free and how many licensable and how many closed to make the whole ecosystem to be vibrant?
Yeah.
Dave, can you repeat the question?
Yeah, so I think the question's around what's it take to have a viable ecosystem, I think. Yeah, so I thought about that a little bit, and so let's just talk about RISC-V because it's the one I know. It's not the only one. So everybody's building processors. there's no shortage of processors. I bet there's 20, at least 20 open processors, and there are licensable processors and proprietary ones. So it's kind of like, processors are fun to build. You know, it's like designing your own programming language. If you're in the programming language, everybody likes to do that. So we're not going to run out of processors. Let's do that. There's this thing called the Uncore, you know, the rest of it. And so, you know, are we, as an open community, going to be able to build the Uncore or not, which are maybe not exciting. So kind of putting my money where my mouth is there's a, you know, Berkeley and Tsinghua in China has long had a relationship. So we have announced that we're going to do something joint together around the Uncore. And so we're going to try and do bus controllers and maybe CAS controllers, the things that nobody else wants to do but are really necessary to do chips. And our take on it, or my take on it is, when we did open source software, there was software patents, and people sometimes would download software and get visits from big companies. So I think part of the challenge will be, in general for open architectures, for open implementations, is to avoid patents. So the approach we're going to try and take is, especially for Uncore things, is look at patents that have expired, or look at papers that were published 20 years ago, so there shouldn't be patents, and follow those to the letter. And we're also going to try and get, you know, legal advice from Tsinghua or Berkeley on how to avoid this. But I think there's kind of this kind of interesting technical thing to do, but there's a flip side of it to actually have impact, is to worry about patents. So like, if you work for a company, they say, don't look at patents, because if they lose, you'll have to pay twice as much. But how are we going to avoid patents if we don't look at it? So I think we're going to have to take a different approach to doing that, and we're going to try to do that. But we're just going to work on the Uncore, but with this goal of trying to complete the RISC-V ecosystem. And this, I mean, I'd say there's plenty of reasons to be skeptical about this, but the success of the software community, you know, where people from competing organizations got together and cooperated on software and share it, you know, it's kind of a positive thing to say about humanity, right? Here we can collaborate for the common good, and it works, even in very
Can I ask a follow-up question? So
Sure.
One of the raging debates in software, open source software, is the difference between free as a beer and free as in freedom. So the idea that, you know, just having open source software is not enough, and, you know, there's proponents for, you know, GPL and copyleft type, and some would argue that helps kind of create an ecosystem where people, you know, out of altruistically contribute, but also have to because of legal restrictions. Do you see any role for that in open source hardware?
Yeah, the questions about copyleft and copyright and so forth, virals. I mean, I see companies react violently, you know, against something that could contaminate all they have. And they just like, I'm not going to deal with that. So I would encourage us to stay away from it. I think people have to be motivated to want to share, and I don't think the copy agreement's going to force you to change your behavior. So since companies can kind of understandably react allergically to it, I would stay with copyright.
Okay. We have another question?
Yes?
So, thanks for the wonderful talk. I had a question about licensable designs. So, from what I understand, most of these are technical designs, or do they also encompass analog IPs? How
Oh, yeah,
are
well,
those licensed?
Well, yeah. My guess is Mark will talk about this. So the people make money on analog IP. There's some company in Oregon that makes apparently all the memory controllers in the world, or something like that. So far this has all been either closed or licensable designs. And analog you need to typically tie to the process. So there's reasons to be like, this will never work, right? On the other hand, at the end of Moore's law, the number of processes and the number of companies is dwindling, right? So if you know, we start stabilizing on some technologies, maybe there's some hope we can get analog IP that, you know, we could share and use. That's gonna be the hardest thing. I think there are people in the Docker project working on that.
Definitely. And I think Mark.
Oh,
and,
Mark is.
I think Mark and Bohr are both going to talk a little bit about
Okay.
some of that.
That's a big challenge. And the other big challenge is CAD software, right? The other big challenge is right now it's very expensive. Back in the day, when Mark Horowitz and I were young, you know, universities built software that was design chips from. So that's another challenge. Yeah.
Sure. So, great conference. There are two questions. One is for fragmentation, because people talk about RISC-V. You can go
Fragmentation.
yeah, go to
possible that some advocates of proprietary instruction sets may expect open instruction sets would be fragmented. It sounds good. So there's kind of two things. Fragmented, that sounds like a bad idea. Like, why did the British drive on the right-hand side of the road, right? There's no advantage. They should have just switched over and be like everybody else, right? So that's kind of arbitrary things. But there's specializations that make sense, right? It's the difference between, you know, a car that can get 100 miles per gallon and a car that can go 0 to 60 in 5 seconds, right? There's specialization. So where we are in computer architecture, as far as I and most of my friends know, is to make progress, we're going to have to specialize. So you have to have, what does this mean for instruction set architecture? You have to have standard pieces that you don't touch because it will screw up the software stack. So there's a standard piece and there's a part where you can innovate. And I think, you know, it's a new idea, but I think that's going to be a necessary going forward. And, you know, we will have opcode spaces that we'll set aside for that. And you know, I think it's not, it's a good kind of debate tactic to bring up. Open source will never work because of fragmentation, but I think the reality isn't that hard to manage.
Okay, great. Let's
Okay,
go ahead and
thanks.
thanks, Dave.